so carrying on with Daniel, we got a question here about how long it'll take Daniel to cross if he rows the boat west relative to the water. Now, west relative to the water, that has to do with the velocity of the boat relative to the water. So I'm going to say that's VBW information, boat relative to water. And he said, in other words, he just sits his boat west and sees what happens. And if I was going to sketch this out, we'd say, okay, here's our boat. I know the dock's straight across, but I'm not worried about the dock. I'm just going to row west, velocity of boat relative to water, straight west. And we know that that information is 10.0 meters per second because we declared it earlier. And we know that the velocity of the water relative to the shore is 7.0 meters per second. That's fine. We know that use a different color. We know that the width of the river itself, displacement, I'll do the displacement in red, in the x direction, was 37.21 meters. And it's asking us how long it's going to get across. It's going to take for him to get across. Well, if the velocity was 100% pointed to the west, and the displacement is to the west, I know, because we've talked about this in a previous lesson, I know that the motion's going to kind of look like this, right? The boat's going to get washed downstream at an angle. But I don't really care about that. All I want to know is how long it takes to get across. And the velocity that allows him to get across is going to be the velocity of the boat relative to the water, which is the velocity represented by those x, the x motion, right? So I'd say, okay, well, the amount of time it takes to get across would be v average in the x direction, which is our 10 meters per second. And we can even say that's v average x in this situation is equal to delta d in the x direction, which is 37.21 meters, divided by delta t, the same isolation method as we had in part C, because it gives us delta t equals delta dx over v average x. We're just cross multiplying. And if we sub in our values, delta t ends up being equal to 37.21 meters divided by, what is it, 10 meters per second. And any number divided by 10 is a friendly one, because you just move the decimal place over one. So you end up saying, okay, well, this takes 3.721 seconds to cross. And we can write it as an approximately equal to, if you like. Approximately, what did we have here? It's just 3 sig figs, I suppose, right? 10.0 is 3 sig figs. So 3.72 seconds. And we could write it there first here. But I want to go into part E. And I feel like it's worth knowing that we're almost finished, so it's part E time! Yeah. Party! Woot woot! Anyway, part E. So how far downstream will Daniel land on the opposite shore if he follows the plan given in part D, which is almost a part E? Part D says that he's going to take this many seconds to go across. But in that time, isn't he also getting washed downstream? And so we expect he's going to land right there, right? That's where he's going to get to the other side. So what we're talking about here is, hey, if this was my river, I got a displacement in this direction, in the x direction, but I'm also getting washed downstream in this direction. What's the velocity that's going to carry me downstream? It's the river, isn't it? So I can say, well, in the y direction, I got velocity of water relative to the shore, which I want to throw out there is v average in the y direction in this case, which is 7.0 meters per second. That's going to be washing me downstream. Well, how long am I going to get washed downstream for? Bloopity bloop. As long as it takes for me to crash into the other side. That's how long. And we just figured out that delta t to crash into the other side, unrounded, mind you, is 3.721 seconds. And so if the question is how far downstream am I going to go, I'm looking for delta dy. This is my question mark, my unknown. I know average velocity in the y direction, and I know how long I'm going to travel for, and notice that there's zero acceleration here, right? So what I could say is, oh, okay, v average in the y direction is equal to displacement in the y direction divided by time. And if I want to get delta dy all by itself, I can do my algebra and say delta dy is equal to v average y times delta t, or 7.0 meters per second, just subbing in these values, times 3.721 seconds. And I think it's going to be somewhere around 26, but can you guys help me out? How far downstream am I going to get washed? Yep. 047? Right. And it looks like, based on my original reference frame, that's going to be south. So remember, we were saying we had north, south, east, west. We let south and west be positive directions and north and east be the negative directions. And then to two significant figures, it looks like. Is it two significant figures or three? Oh, I suppose it's three, isn't it? No, it's two because of the 7.0. Nuts. So therefore, the boat lands 26 meters south of the dock, on the west side of the river. Now, as a follow-up to this, I've got a quick little set of questions here. I want you guys to take a second. I want you to talk with a partner. I'm going to zoom in here. Talk with a friend and sort this one out. I've got three boats, A, B, and C, and there's three questions. I, and I. See if you can answer the questions, okay? Talk with a friend. Go.
Which boat?